we have a few, like we'll have another help session after this one. So if you're watching online, I want the notes for it by the beginning of the exam. I mean, y'all don't have to do the notes, of course, but then also there's a seminar this afternoon at 4:30. It's in this building downstairs in 104. It's our senior seminar. I think it'll be quite interesting. Brooks Barrios is talking about his work with nano silver. I think he was working with Dr. Alivio, if I'm not mistaken. And then Tina Lowe is, it was like a paper review. She's going to talk about the chemistry of cold and hot brew coffee. So that is also worth extra credit. I'm pretty sure that I'm going to be there, but as usual, if I'm not, you can just take a picture of yourself at the seminar. Yeah, I'll send an announcement out about that. And then we will have another help session. So that's 3 more opportunities for extra credit. This help session, the next help session for the final, and then also this seminar. I think this is our last seminar of the semester. All right, I wanted to go over the free response again, just to make sure that everybody's clear on what we're doing with free response, and then we can address any particular questions that you might have. Let's see. I was hoping to find a question. Yeah, I don't have a good question that's just like what you're going to see on the free response. So let me I'll sort of show you I'll make up an example. Is that okay if I just make up one? But it'll be like what you'll have on the free response, except different shapes perhaps, different numbers and what have you. Yeah?
This is when do you think you'll have our grades for this morning?
I'm getting pretty close.
Oh, okay.
So hopefully this afternoon, but it might be tomorrow. Okay? All right, so 3 free response questions. The first one has 2 parts, and it is a Newton's law problem where I give you a shape. Say I give you a bar, for example, that's rotating about this axis. I would not give you a bar. Or it might be a bar, but it's some shape. If it were a bar, I would give you the length. Let's say that it's 2 meters in length, and then the mass I would give you, we'll say that it's 3 kilograms, and then I give you a couple of forces. In this case, I'm just going to give you a force like this, and we'll say that this angle is equal to 30 degrees, and that it's 4 newtons. And I ask you a couple of questions. I first ask you, what is the net torque? Actually, let's go ahead and do another force on this as well. So let's say that there's a second force right here that has a force of 2 newtons. Okay? And I ask you 2 questions. First, what is the net torque? So part A, I think that's the first question. Yeah, what is the net torque is the way that I would phrase it. And you'll probably see some of this on the multiple choice too. Now, the first thing that you need to do is to determine which torques are positive and which torques are negative. So I'll call this torque 1. Notice that this torque is causing a motion in this object that is, what's that, counterclockwise, right? You'll see that that's counterclockwise, so that's going to be a positive torque. This torque, torque 2, causes a clockwise torque, so that's a negative torque. So my net torque then is going to equal to torque 1 minus torque 2. So you could have a third force, you could have a fourth or a fifth, you'll probably only have 2 or 3. Just FYI, so if I have a force that is acting at the axis of rotation, no torque at all, because R is equal to 0. Or if I have a force that's acting along the length of the moment arm, no torque at all, because it's acting at an angle of 0 or 180 degrees. Hey, good morning. All right. So the net torque in this case is going to be torque 1. That's going to be 4 newtons times this distance. Be careful on your diagrams that I gave you the length of the bar, but really I need to know this distance, which is 1 meter. So that's my moment arm, R, times the sine of 30 minus 2 newtons times 1 meter. And so that's going to be equal to 2 minus 2. Oh, that's equal to 0 Newton meters. Oh, shoot. Okay, let's Not moving, yeah. So let's say that this is instead 8 newtons, just so we get a little action going on here. And so that gives me 8 times a half, that's going to be 4. And so let's imagine that this is 2 newton meters. Okay, I just changed this force to 8 newtons. So I'm winging it here, okay? But your question will be very similar. What is the net torque? And the answer to this one would be 2 newton meters. Okay? So the next question, which would be a follow-up question, would be what is the angular velocity after a certain amount of time? And let's say that that time is, I don't know, c equal 4 seconds. What is the angular velocity? And of course, when I ask for angular velocity, I'm asking for what is omega. There are a couple of steps that you need to do in this. And the first step is that you just need to find the moment of inertia. And for a bar, that's equal to 1/12 mv squared. So that's 1/12 of the mass, which was 3 kilograms, and the length, which is 2 meters squared. And so that's equal to 1 kilogram meter squared. Okay, so that's my moment of inertia. I know what is the net torque. The net torque is 2 newton meters, counterclockwise, by the way, because it's positive. And now the next step that I need to do is to figure out what is alpha. Alpha is torque over the moment of inertia. That just comes from Newton's second law, which is on your equation sheet. Torque equals I alpha. And I solve that for my acceleration. So that's going to be 2 divided by 1. 2 divided by 1. That's equal to 2 radians per second squared. Really, I want to know what is omega after 4 seconds. Omega is equal to omega naught plus alpha times t. That's 0 plus 2 radians per second squared times t, which is, what did I say it was, 4 seconds. So that's going to be 8 radians per second. So that would be the answer. Several steps to that part. I have to find the moment of inertia, find the angular acceleration, and then find omega.
So would we just assume that it was at rest to start?
Yeah, I think I say that. But if I don't say, we'll just assume that. Okay? I do not say that. But let's. Yeah, we'll assume that it is. Okay? All right, that's the first free response. Something really similar to that. I mean, it'll be a different shape and different numbers, but otherwise the same. The second free response will be an energy problem. So I'll have some object. Let's say that it's a cylinder that is rolling with a certain velocity. Let's say that the velocity is equal to 4 meters per second. And let's say that it has a radius of 1 meter. And there's a couple of things that I want to know. I want to know what is the total energy, the angular speed, and then, well, we'll get to the third part. The first thing is I want to know what is the angular speed.
Oh, I thought it was.
Yeah, I know I said total energy, but the first part was what is the angular speed? That is, what is omega equal to? All right, I know V and I know R, and I know that V is equal to omega times R, so omega then is equal to V divided by R. That's 4 meters per second over 1 meter. That is 4 radians per second. That would be the answer to that part. Then the second part, part B, asks what is the total energy of this rolling object. And just like we did in class, this thing has 2 types of energy. It has a translational energy, and it has a rotational energy. Okay, translational and a rotational. And then that will be equal to our total energy. That's going to be 1/2 I omega squared plus 1/2 mv squared. Now I know omega, but I don't know I, so I need to do that over here. I'll do it off to the side. This is a disk or a cylinder, and so it's 1/2 mr squared. See, I would give you the mass. Let's say that the mass is 2 kilograms. Okay, So I would be 1/2 of 2 kilograms times the radius, which was 1 meter. Goodness bless you. And so that's 1 kilogram meter squared. Okay, so I have to figure out the moment of inertia. In fact, on most of these problems, when you have a rotating object, you're going to need to find the moment of inertia. I usually just do that right up front. All right, so now I can figure out my total energy. That's going to be 1/2 of I, 1 kilogram meter squared, times omega squared. We found that omega was 4 radians per second squared, plus 1/2 of the mass, which was 2 kilograms, that's given, times the speed, which was 4 meters per second. Make sure you square those numbers, the ones that are squared, so that's 8 plus 16 equals 24 joules. That's the second problem. Now, the third problem, the third part of this, is that what if there is a force applied at that point? Let's say that that force is equal to 2 newtons. And I want to know how far does that wheel rotate, through what angular displacement does it rotate before it comes to a stop? So this has to do with the work energy theorem. I know that work is equal to a change in energy, and if I have a torque acting over a certain displacement, that is equal to my change in energy. Or my torque times theta is the work that's done by a torque. Remember, work was F times D, force times distance. In a similar way, it's also torque times theta. So my torque is equal to F times R. The force that I have up here is 2 newtons acting at 1 meter. So that's 2 newtons, 1 meter, 2 newton meters. Doesn't matter if it's clockwise or counterclockwise. What's really all that's important is taking energy away. It's like a braking force.
And what is the question here?
It's asking, what is the angular displacement, sorry about that, what is the angular displacement before it comes, or as it comes to a stop? That is, I want to know what is theta equal to. I'm applying a force. Oh, let me read it to you exactly, actually.
Because I'm just like, because we're adding this new force here.
Yeah, so I say you apply a force of blank newtons tangentially. That means at no angle. So you know it's just theta is 90 to the surface of the object. What is the angular displacement of the object before it comes to rest? Okay, y'all get that? You want me to say it again? All right, you got it. All right. So that torque I know is 2 newton meters. 2 newton meters. Theta, I want to know what theta is. I know E is 24 joules. I found that in the previous part. So theta is going to equal to 12 radians. It's going to spin through 12 radians before it comes to rest with that braking force, which is providing that torque. Alrighty? All right. Let's do the third question. Remember, all the free response come from chapter. Yeah. Third one is an angular momentum question. We good, Jackie? Awesome. You're gonna have a rotating object. Let's say that it's a, I don't know. We'll just go with a bar still. So I have a bar that's rotating. I'll give you the angular speed. So let's say that the angular speed is 2 radians per second. This is, I don't say it's omega, I say it's the angular speed. That's what this is. You bring a second object Okay, I'm going to tell you sort of what, I haven't told you this yet. It's secret. You ready? So I said actually you're going to have 2 objects coming together. That is true, but actually it's going to be a discrete particle. We've done questions like that, right? Y'all remember doing those where you have like a kid that jumps onto the edge of the merry-go-round, or you have this object that comes together. So this object is spinning at 2 radians per second, but then I bring another object and it jumps onto the end of this bar, and I want to know what is its new angular speed. All right, I give you the mass. Let's say that the mass is 4 kilograms, and I'd have to give you the length of the bar. The length of the bar, let's say that it's, we'll say it's 4 meters.
And this is a combined mass?
No. That's just the dimensions of the bar. Okay? And then the second object, let's say that it has a mass of 2 kilograms. I'll call this M2 and call this M1. All right, the first question I want to know is just what is the angular momentum of the bar? That's angular momentum, not angry mom, as some of you might think. Okay? The angular momentum of the bar is going to be equal to L equals I times omega. I of the bar will be 1/12 mb squared. That's on your equation sheet. So that's 1/12 of the mass, which is 4 kilograms, times 4 meters squared. That's what I got from right here. What's that? 16 over 3. 5.3. Sorry, I should get some easier numbers. So it's going to be 5.3 times omega, which is 2 radians per second. So that'll equal to 11 kilogram meters squared per second. So that would be the first answer. Just what is the angular momentum? This first object, before this second object ever comes into play, what is the angular momentum? That omega does have to be in radians per second. I give it to you in radians per second. So all the units are all good. Okay? The second part is what is the total moment of inertia? Again, mom is moment. The total moment of inertia, that's an abbreviation. What is the total moment of inertia? I have two objects coming together now. And so the total moment of inertia is equal to I1 plus I2. We've already done the first one. That was that 1/12 mb squared. But then the second one, I'll have just mr squared. So this is equal to, we found it to be, what, 5.3 plus the mass that's right here, which is 2 kilograms, times the distance from here to here, that's 2 meters, because the total length is 4 meters. It's 2 times 4, 8, 13. 13 kilogram meters squared. So that's the combined moment of inertia, and that's part B. And then finally, what is the final angular speed? So we say Li equals Lf. Li I've already found, it's 11, that's this quantity, equals to Lf is going to be my final moment of inertia times omega final. And that final moment of inertia I've already found, it's equal to 13 times omega final. So it's going to be 11 divided by 13. Oh, hold on just a second, let me write this down. Sorry, it's a good question. I'm sorry to tell you. So this last question is, what is the speed of the disk of the object after the mass is placed? Or I say, after placing the object, I say. After you add this extra mass onto the object, what is the new angular speed? It's going to slow down. I want to know how much does it slow down. And it goes from, what was it before? 2 radians per second to 0.85 radians per second. Okay? Y'all get on those? We've done variations of all of those, so you can find similar problems in all the tests, but I don't think there are any that are exactly like this. So I just want to make sure that everybody's clear and on the same page. 100% on those, okay? These are the questions, different numbers, different shapes, but otherwise exactly the same. 100%? You get a promise? Can I get a promise? An amen? Something? All right. All right, what do y'all want to look at for past exams? Past exams? Hey, you said we're okay? Okay? Okay. Past exam. He's like the nicest guy you've ever met. Hello, Dr. Dave. Nicest guy you've ever. I love that man. He's awesome. He's like one of the world's best computational chemists. You know this? He has like 100, almost 200 publications. Does that mean anything to y'all? It's a lot. It's a lot. Like for even a big, if he was at like a big university like UT Austin or University of Michigan, that would still be a lot. He's just really good at what he does. He's a good teacher too. Anyway, so what do you want to look at? Particular questions? I can sort of scroll through. Let me go to some of the newer exams. They tend to be more indicative. Chapter 9, okay.
And these are all from chapter 8.
Yeah, the free response are all chapter 8. Let's see, this is fall 2020B. This was all chapter 9, so it's a good one to practice chapter 9. There's Archimedes' principle, equation of continuity, and Bernoulli's principle. You need to know what each of these principles are, what they mean, how they're applied, and then also what is the underpinning of them. That is, Bernoulli, let's test you. Bernoulli is based on the conservation of what? Starts with an E. Energy, right? Bernoulli, that says that if the velocity goes up, the pressure goes down. They're inversely related. Whereas the equation of continuity, which says that the area times the velocity of a fluid is always constant, that's based on the conservation of, starts with an M, matter, right? Pascal's principle is based on the idea that a pressure felt at one point in a fluid will be felt at any other point in the fluid. And then what's the other one? Archimedes' principle is based on the idea that the buoyant force is equal to the weight of the displaced fluid. All right? You need, hey, no, go ahead. I'm done. On number 17, on which test? Yeah, that's this one we're on. So 17. You're going to have one like this. I was just about to say this, actually. So manometers, usually manometers and barometers. I want to know here, what is the pressure P? The first thing when you encounter one of these is ask, is this pressure, is it bigger or smaller than this pressure? And you can tell by the relative levels of the fluid in the manometer or the barometer. This is a manometer, but a barometer is really similar. Barometer, by the way, is just different in that P naught is 0, is a vacuum, and a manometer is not. So the one with the lower level, that's the bigger pressure. The bigger pressure pushes that fluid down to a greater depth. So P is bigger than P naught. I know that P naught is 1 atmosphere, so I can get rid of some of these answers. I can get rid of those 3 answers. And then you could probably guess what the answer is from this point, right? Yeah, you could guess and be almost certainly true that it, and be almost certainly certain that it's B. Well, let's just calculate it and we'll see. So P is bigger than P naught, so I know that P is equal to P naught plus or minus rho GH. In this case, that plus or minus is going to be plus because P is bigger than P naught, so P is equal to P naught plus something extra. And so that's going to be equal to 1 atmosphere, or 1 times 10 to the 5th pascals. You do need to do that conversion into SI units, and pascals are the SI unit, plus rho. It's mercury, so you look on your equation sheet, there'll be a table with some densities, and it'll have that 13,600 is the Yeah, 13,600 is the density of mercury times G, which is 10, times H, which is this distance, 0.1, and I get 1.1 atmospheres. It's actually 1.14, but 1.1 atmospheres. Okay?
So why do you have to convert it into pascals if your answers are in atmospheres?
Because this calculation right here comes up in pascals.
Okay.
Yeah, good point there. Okay, so be careful with that. You're never going to go wrong with SI units. So if you ever have any question, just convert everything to SI units and then check the units in your answers.
Conversion on the equation sheet?
I think it is. Yeah, whatever's on the equation sheet you'll have. I'm pretty sure that it is. But it's really easy to do that conversion, to convert from pascals to atmospheres. Look, you just get rid of that, and then it becomes atmospheres. Okay? Um, yeah, good question. Let's look at some of the Archimedes principle. Is that okay? Archimedes. This one has a lot of questions on it because I split that exam 4 into 2 pieces. Might do this next year. Would y'all like to have exam 4 split into 2 pieces? No. Some of you might like it. It gives you an extra exam. Um, what do y'all think about having the exam on this Wednesday? Do y'all like doing that on tomorrow? Does anybody like having?
Have 2 exams on the same day?
Huh? You like that?
I thought that I didn't have
Yeah,
okay
like
no
I
physics.
doubled up yesterday, but other than that, I don't know.
Do y'all have exams on Thursday? You do.
That's like the only day.
That's
I don't have
the bummer, right? Yeah.
What's
Be-
wrong with having it on Wednesday?
Well, if you have an exam on Thursday, then it's a crunch to get them all done.
Oh, I have an exam every day this week, so it doesn't matter.
I have an exam every day except for Thursday.
Oh man, I'm sorry. I always hated exams. I always felt like my grades would take a dive bomb in exams. I know not all of y'all are like that. Some of y'all are like, you love final exams because you're going to do so great on them. But most normal people don't do so well under the stress of final exams. But they are important, okay? So get a lot of rest, pace yourself, spread out your studying, make time for them. All right. Let's look at, oh, what's a good question? No, none of these are very good. Let me go look at a different test. We'll look at some Archimedes principles. Yeah, I don't have any good ones here. Okay, let's look at 19. You won't see one exactly like this, but it's a good one to think about with Archimedes' principle. I want to completely submerge a block of ice. You know, if you have ice, because ice is less dense, it floats, right? Y'all have had ice in a drink before and it floats. Actually, the density of ice is really close to that of water, so it usually floats right up at the top with just a tiny little bit of it sticking up above the level of the water. So, but anyway, it usually floats like that, and I want to know what force is required to push it down like that. Now, there is another force, the buoyant force, which is pushing up. And so I need to have a force that's big enough to overcome that buoyant force. So here, I want to know what is the buoyant force. If I completely submerge this ice, if the ice is completely submerged, what is the buoyant force that will be acting on it? And that's going to be equal to the density of the fluid times the volume of the object times the acceleration due to gravity. You want to know what test this is? It's the Fall 18 exam. Thank you. Fall 18. So here, this is a little trickier because I'm not given the volume of the object, but I can find the volume of the object because I know that it's ice and I know its mass. So since density is mass over volume, volume is mass over density. And the mass of this is 0.5 kilograms I don't know the density of ice off the top of my head. It's on your equation sheet though. What is it? 917. Yeah. Okay, thank you, Shelby. 917 kilograms per cubic meter. You'll probably have a question too, by the way, that's just a density question. That's 0.00055 cubic meters. So that's going to go into my volume of the object. So it's going to be the density of the fluid, which is 1,000. That's for water. 0.00055 times 10, which is 5.5 newtons. So there is a 5.5 Newton buoyant force acting up. There is also a 5 Newton force, which is just the weight of the block acting down. So that means that it's going to be 0.5 newtons. Yeah.
How do you know the difference between this problem and like the other problems where you have to do some of the forces like FP minus FW or minus W?
Okay, let me, I glossed over what I just said, so let me go back on what I just said and explain. I'll come back to your question, okay? So, notice here that if I have this object that is fully submerged, there is a 5.5 Newton buoyant force acting up, and there is a 5 Newton force acting down. That is equal to the weight of the ice. So I need an additional force. This is the force that you have to push down on, of 0.5 newtons. And so that's why the answer is 0.5 newtons. Bryce, you're asking about apparent mass questions, right? Is that what you're asking about?
Yeah, like about like how you have to do like F. I don't know. It's a certain problem.
F equals FB minus FW, basically, what you just did.
Yeah, that's what I just did. Yeah. Well, I mean, if I have, well, you're always going to have to do that. If I have a weight of the object that's acting down.
So what you could do without having to follow that formula, FB equals PG.
No, you're always going to find the buoyant force, you're always going to have to use this. Yeah. That answer your question?
It works.
Okay. All right. All right. Again, know what Archimedes' principle is, sort of know the idea behind it. It's the weight of the displaced fluid. Be able to solve for the buoyant force. Let's look at equation of continuity too. This number 21 right here. Oh wait, no, never mind. You're not going to have one like 21. You're not going to have any question where you have to use Bernoulli's principle in equation form. This is Bernoulli's principle. We didn't do that in class anyway, so if you saw something like that, it might look a little foreign to you. But you're not going to have any questions where you have to use that formula to solve for something. But you will have Bernoulli's questions. What is the Bernoulli principle based on? Conservation of energy. What happens to the pressure of a fluid as the velocity goes up, the pressure goes down. Those sort of application type things you'll see. Okay, but you're not going to have to calculate anything with Bernoulli principle. So if you see something like that on the exams, and you know you won't see that, like this number 21. This is a good application of Bernoulli's principle. We did that in class yesterday. What happens to the smoke? Right, it rises more quickly because it creates that low pressure above the chimney. You're going to have Pascal's principle with some sort of hydraulic press, like number 24. Pascal's principle is based on the idea that a pressure felt at one point in an incompressible fluid is felt at every other point in that fluid. So if I apply a pressure here, that pressure is felt at every point, including over here. So I would have F1 over A1. That pressure at point 1 is equal to F2 over A2, the pressure at point 2. So I have all those values. I just have to pick them out of the words. F1 is 100 newtons. A1 is 1 square meter. A2 no, I'm sorry, A1 is 0.01. See it? It's the smaller piston. A2 is 1 square meter, and I want to know what is the force that's given on the right-hand side of this hydraulic press. So that's 10,000 newtons is the force that you get out. So you get the big force out of the big piston and the little force out of the little piston. Okay? Did somebody ask something? No. Any particular questions? Jogging your memory about anything here? No? Y'all feel ready for the test? Not yet. Chapter 8 is a big review of everything that we've done so far. So if you've been doing well so far, then Chapter 8 should be relatively not that difficult. But I know that some students have struggled in the first couple of exams, and so you might need to spend a little extra time. It's similar material. It's not quite as in depth, but it's similar material with energy and momentum and Newton's laws and kinematics. All right. Well, yeah. Austin, go ahead. Number 14. Right here? Yeah. So what minimum force must be applied to lift the object? This is a balance of torques, kind of like we did in lab, those of you that are in lab. But the torque on this side has to be equal to the torque on this side. Now there's a force here. That's equal to 120 newtons, because it's a 12 kilogram mass, so it has a weight of 120 newtons. And I know that this distance is 3 meters, and this distance is 1 meter. So I'd say torque on this side equals torque on that side. In order to be balanced, those torques have to be equal. F times 1 equals 120 times 3. So F then is equal to 360 newtons, which you can sort of think about if you've ever used a lever like this or on a seesaw, that you need a big force if you're close to the fulcrum, close to the axis of rotation. Right. You'll certainly see questions, I'm pretty sure that you'll see questions like that. Anything else, y'all? Okay, well, listen, I have lab this afternoon, so I'm going to be out for much of the afternoon. But if you want to come see me, just send me an email. I'll try to make some time. I'm giving an exam, so I might be able to see you while I'm giving an exam. But otherwise, I will see you tomorrow. I'll be around in the morning. I get in about 8. I'll be around until 10:30.